Hello everyone, welcome to this lectures in differential calculus. Today we are going to talk about functions of two variables and functions of three variables, and we'll also talk about level curves and level surfaces. So we have already in the previous lectures talked about functions of one variable. Okay, so the real valued functions of two or three variables or even several independent real variables are defined in the similar manner. Okay, as we did for the functions of one variable. So let us first define the functions of two variables. So a function f of the two variables x and y is a rule that assigns a number f of xy to points xy of the xy plane. Okay, so if there are uh, points on the xy plane which are written as a ordered pair x comma y. Okay, so for every for such points, if there is a rule assigned f which gives or assigns a number fxy corresponding to the points xy in the xy plane, then we call this as a function of two variable. Okay, so for f to be a rule which assigns a number fxy corresponding to points in the xy plane, then we call this as a function. Okay, so and for every point on the xy plane for which this function takes real value, we the set of all such points will be the domain of the function. Okay, so a function fxy is the value of the function at the point x comma y, and the set of all such points where the function is defined is called its domain. Okay, and the range will be the corresponding values of the function. Okay, so fxy corresponding to point ab, if we get f of ab, so set of all these values which we get by this rule, though set of these values is called the range of the function. Okay, so the range of the function is the set of its values fxy for every point xy in its domain. Okay, so this definition of function is uh, very similar to the function of a single variable, where the say f of x was a function of single variable x, and x are the points on the real line, and we get corresponding function values. Okay, so here the input values or the values of the domain lie on the xy plane. Okay, so corresponding the function value will lie along the third axis, so that means we can draw the function in a space xyz space. Okay, and for a function of one variable, when x was input and fx was the corresponding output, then we saw that the we can draw that in a xy plane, and those are curves. Okay, so similarly, when we have a function of two variables and we our domain is xy plane and the corresponding function points are along the third axis, so we can draw this in space, and now these are not just curves, these are actually the surfaces. Okay, so the graph of a function f with two variables x and y is the surface z is equal to f of xy. Okay, formed by the points x y z in the x y z space with x y in the domain of the function. Okay, so for every point in the domain we will get a corresponding function value on the z axis. Okay, on the height, and so they will form a surface z is equal to f of xy. Okay, uh, so this was definition for a function of two variables. Similarly, we can extend it for three variables, that a function f of three variables x, y, z is a rule that assigns a number f of x, y, z to points x, y, z of the x, y, z space. Okay, so in one variable the input variable was on a line. In two variables the input was on a plane xy plane, and in three variables, okay, the input points are points of this space. Okay, so for every point in the space for which the function value can be assigned, uh, this will be a point on the fourth direction. So to graph this function we require a four-dimensional space, we actually which we cannot do a sketch on a paper. Okay, so this is an important note that the graph of the function of three variables, which is w is equal to f of x y z, lie on a four-dimensional space which we cannot sketch in our three-dimensional frame of reference. Okay, so but yes, we can extend it, and we can further extend it to say n variables. Okay, so if you have x1 x2 x3 so on xn as uh, n independent variables, and we can define a rule f such that it gives assigns a corresponding number f of x1 x2 so on xn. Okay, so this can be further extended to uh, uh, n dimensions. Okay. Okay, so let us see few examples on what will be the domain and range of certain functions. Okay, and to start with the say first function, or this function is z is equal to root of y minus x square. So domain will be the all values in the xy plane for which the corresponding z values uh, are possible. So for a root we know that what the terms inside must be, this root must give a positive, so this y minus x square must be positive. Okay, so a domain in the xy plane is such that this quantity inside root must be positive. So y minus x square must be greater than equal to 0, or y greater than equal to x square is the domain of this function. And for this domain the root values are 0 or greater when y is equal to x square, then it is 0, and y is greater than equal to x square, so it is root of positive, which will be any number positive. So range is 0 to infinity. So if we plot the domain on the xy plane, then uh, domain is all y values which are greater than equal to x square, and y is equal to x square is a parabola. Okay, so this is y is equal to x square, so all values which lie in this region are in the domain, because these are the points where y is equal to x square is satisfied. Okay, and so these points will be outside the domain where y is strictly less than x square. Okay, second function that I chose is z is equal to 1 by xy. So domain of this function will be all points except where xy product is non-zero. Okay, so domain or all points in the xy plane except the x-axis and the y-axis. Okay, and the corresponding range is all z values except the origin. Okay, so correspondingly this will be the range minus infinity to 0, and its union with 0 to plus infinity. Okay, the third function is z is equal to sine of x y. Okay, so this function is defined for every xy, so the domain is the complete xy plane. Okay, and for every xy the sine lies in -1 to 1, so its range value is -1 to 1. Okay, the fourth function is z is equal to y by x. So this function is defined for all xy in the plane except where the denominator is 0. Okay, so domain is all values in the xy plane except the points where x is 0, so x must be non-zero, or you can say domain is all points on the xy plane except the points on the y-axis. okay, and correspondingly z can take any value, so range is minus infinity to plus infinity. And one last function is z is equal to log of x square plus y square minus 4, and the domain will be all points in the plane where this x square plus y square minus 4 is positive. Okay, so domain is this x square plus y square is greater than 4. Okay, and corresponding range will be log will take all values, so minus infinity to plus infinity. Okay, so we'll just plot this, okay, the domain of this function. Okay, so we know that x square plus y square equal to 4 is a circle, okay, of radius 2. So domain is all points outside that circle. Okay, so domain is all these points which lie outside this circle. Okay, and the points on the circle are also not part of the domain because of the strict inequality here. Okay, and the points inside are also not in the domain. So we have seen two graphs here. Okay, one is where the uh, points on the boundary are part of the domain, and this case where points on the boundary are not part of the domain. Okay, so we'll talk about few more definitions here. Okay, the first one is what are the interior points of the domain. Okay, so this is for functions of two variables, and we can extend it to three or higher variables. So first is the what are interior points. So a point x naught y naught, okay, so we are talking about two variables in a region R in the xy plane is an interior point of the region if it is the center of a disk of positive radius that lies entirely in R. Okay, so any point in the region will be called an interior point if at that point we can draw a disk centered at that point such that every point in the disk lies uh, entirely inside the region. Okay, so if it is possible to draw a disk with center at this point and such that every point of the disk is entirely in the region, then we call this point as a interior point. Okay, the other possibility is the boundary point. Okay, a point x naught y naught is a boundary point of region R if every disk centered at x naught y naught contains points that lie outside of the R as well as points that lie in the R. So any point will be called a boundary point if at that point we draw a disk. Okay, and for every disk that we can draw with center at this point, there that disk consist of points which are inside the region and consist of points which are outside the region. Okay, so if this is true for every disk that we can plot with center at that point, then that point is called the boundary point. Okay, so these are two definitions. Okay, so for interior point, if it is possible to draw at least one disk of positive radius such that every point is inside, then it is an interior point. And for a boundary point, if we every disk that we draw with center at this point contains points which are outside and inside, then we call it a boundary point. Okay, now based on whether the points are whether the boundary points are there in the domain or not, we can call the region as a open region or closed region. Okay, so first it is important to note that the boundary point itself need not belong to the region. Okay, as we saw in the previous example, x square plus 4 square x square plus y square strictly greater than 4. Okay, so the points on the boundary of circle were not part of the domain. Okay, but still it is a boundary. Okay, so open region, a region R is open if it consists entirely of the interior points. Okay, so any region we will call it open if it contains only the interior points. Okay, And for example, open unit disk. Okay, so all the points xy which satisfy this equation that x square plus y square is strictly less than 1. Okay, so it will be only interior point, the boundary, which is the boundary will be a circle, x square plus y square equal to 1, and no point of the boundary is part of this region. Okay, so it is a open disk. Okay, and it is open region because all the points are interior point. That means if you choose any point in this region, and then you can draw with that on that point a disk centered at that point, such that all the points in the disk will also lie entirely inside this disk. Okay, so it is a open region. Other is the closed region. Okay, so a region is closed if it contains all its boundary points. Okay, so for example, the closed unit disk. Okay, so there is a equality also. That means the boundary is a circle. Okay, x square plus y square equal to 1, and all the points on that circle are part of the domain. Okay, so it is a closed unit disk. So if you start with something like this open unit disk, and if you add some boundary points but not all boundary points, then we can also say that there are domains which are neither open nor closed. Okay, for example, in this open disk you just add say few points of the boundary which also become part of domain, then it is not open because there are some boundary points, and it is not closed because all the boundary points are not there. Okay, so it will be neither open nor closed. The third definition is whether the region is bounded or unbounded. So a region in the plane is bounded if it lies inside a disk of finite radius. Okay, and a region is bounded if it is unbounded if it is not bounded. So any region or domain we will call that as bounded if you can draw a disk of finite radius such that the complete domain lies inside that disk. Okay, and it is unbounded if for any disk you draw of any size there are points which are outside that disk from the domain, then we will call it unbounded. For example, a bounded set in plane will include line segments, triangles, interior of triangles, rectangles, interior of these circles, interior of circles, disk, interior of disk. Okay, so for example, if you have a line segment, that means uh, and it will have fixed endpoints. Okay, so fixed distance, so you can always draw a disk of larger radius such that this line segment lies entirely inside that disk. Okay, so we'll call this as a bounded region. Okay, similarly triangle, so if you have any triangle you can draw a disk such that the triangle completely lies inside that uh, disk. Okay, so we call that triangle as a bounded region. Okay, and so on. Similarly, we will have unbounded sets or unbounded regions in plane, like line, coordinate axes, graph of functions defined on infinite intervals, the quadrants, the first quadrant, second quadrant, so on, and half planes. Okay, so plane above the x-axis or plane below the x-axis, plane to the right of y-axis, and so on, and the whole plane, whole xy plane itself. Okay, so in all these cases doesn't matter how large you take the disk. Okay, there will be always some points which will lie outside the disk. Okay, so if there is an infinite line, so you choose any large size disk, there will be points on the line which will be outside that disk. Okay, so these are all examples of unbounded sets or unbounded region. Okay, so now I take two examples here. Say describe the domain of the function fxy is equal to root of y minus x square. So we just said that the domain will be all those points for which y minus x square is greater than equal to 0. Okay, so the parabola y is equal to x square forms the boundary of this region. Okay, and so if I plot this region, it will be this will be the interior points, and there will be boundary, and boundary is also part of the domain. So domain consists of all the interior points and this boundary. Okay, So these two combinedly makes the domain of this function, and all these points here will be outside the domain for which y minus x square is strictly less than 0. Okay, so this domain is closed because all the boundary points are part of the domain. Okay, so y is equal to x square is the boundary and which is also part of the domain. Okay, so it is a closed region, and it is unbounded region. Unbounded because it doesn't matter how large disk you take. Okay, there will be point in the positive direction of y-axis which always lie in outside the disk. Okay, so it is not possible to uh, draw a disk of finite radius which will contain all the points of the domain. Okay, so this is the unbounded region. Similarly, I take, say, for example, describe the domain of the function f of xy is equal to log of 9 minus x square minus y square. Okay, so on the xy plane, the points which will be in the domain will be such that this quantity 9 minus x square minus y square is positive, strictly greater than 0. Okay, so it will give us that x square plus y square should be less than 9. Okay, so so function is defined only for these points, so this will form the domain of the function. Okay, and so all points x comma y which satisfy this equation, okay, will be in the domain of function. And so you can see that this is if there is a equality, it will be a circle of radius 3. So this means all the points lie inside the circle of radius 3 will be in the domain of function, and the points on the circle are not part of domain because there is a strict inequality here. Okay, so the circle, this is the boundary of the domain. Okay, so as I said earlier that even this the boundary may not be the part of the domain. Okay, so still this circle is the boundary, but it is not part of the domain itself. So this domain is a open domain. Okay, open because all the points are interior points of the domain. There is no boundary point which is part of the domain. Okay, and it is a bounded region because we can construct a disk of finite radius. Okay, such that all the points of the domain lie inside that disk. Okay, so you can easily see that with center at origin, say, we can draw a disk of 5 radius. Okay, so that all the points of this region are entirely inside that disk. So this disk is a this region is a bounded region. Okay, so this, for this function, the domain is this, and it is open and bounded. Okay, so now we can extend these definition for functions of 3 variables. Okay, so as I said that any point will be interior point for function of 2 variable if we can draw a disk centered at point such that all the points in the disk are inside the region. Okay, because in functions of 3 variables, instead of xy plane, the domain is in space xyz space. Okay, so any point xy, x naught, y naught, z naught in space inside the region R, in a region R in this space, is an interior point of R if it is the center of a solid ball that lies entirely in the R. Okay, so the definition is very similar to 2 variable, but in case of 2 variable, domain was in plane, so we said that if we can draw a disk. Okay, but now we are in space, so here if we can draw a solid ball centered at this point such that all the points inside the solid wall lies entirely in the region R, then we say that all such points are the interior points. Okay, and similarly for the boundary points, a point, this will be a boundary point of the region if every solid ball centered at this point contains point that lies outside the R as well as inside the R. Okay, so if this point will be a boundary point if if we consider this as the center of a solid ball, and some points lie inside the region and some points lie outside the region when we construct such solid wall using center at this point. And if this is true for every solid ball that we construct, then we say that this is a boundary point. Okay, so again the boundary point itself need not belong to the region. Okay, the other definition, okay, remain the similarly. For example, open region. Region is open if it consists entirely of the interior points. For example, interior of a unit sphere. Okay, so for example, all point x, y, z such that this is satisfied. Okay, so it is the interior of the unit sphere. Okay, so if you choose any point here, we can construct a solid wall centered at that point such that all the points in the solid wall are inside this region. Okay, so this is a open region. Okay, because every point is a interior point. And the region will be closed if it contain all its boundary points. Okay, so for example, closed unit sphere. So if uh, this is the closed unit sphere, that the boundary points are also part of the domain. So x square plus y square plus z square equal to 1 is the boundary of this sphere, and all the points are part of the domain, so it is a closed region. Okay, so again we can have regions which are open, which are closed, or which are neither open nor closed. For example, if in this uh, unit sphere I add some boundary points but not all the boundary points, then this will be neither open nor closed. Okay, so similarly we can define the bounded and unbounded regions as well. Okay, now I draw some known graphs so that we can utilize them in our future lectures. And first are the planes in 3 dimensions. Okay, so the first is the z is equal to 0 or xy plane. Okay, so you can see that this is the z is equal to 0 plane, which lies, or we can also call it xy plane. Okay, so for z is equal to 0, for all points xy in the domain, the corresponding value of z is 0. Okay, so this is the xy plane which passes through the x-axis as well as y-axis. Okay, and at each point the value of z is 0. Okay, similarly we can have other planes like x is equal to 0 or yz plane. Okay, so for every point uh, eh, x is equal to 0 means the values are on the yz. Okay, so this plane uh, which passes through the y-axis and z-axis. Okay, and similarly we can also define the xz plane or the y is equal to 0 plane. Okay, so y is equal to 0 or xz plane means all the points lie on this plane which passes through the x-axis or z-axis. Okay, so these planes are uh, parallel to uh, the is perpendicular to the y-axis. Okay, and they pass through the x-axis as well as the z-axis. Okay, so similarly we can define uh, any plane parallel to the xy plane by taking z is equal to constant. Okay, and if that constant is positive, then that plane will be parallel to this plane above the axis, and if a constant is negative, then that plane will be parallel to this and below the axis. Okay, similarly x is equal to constant are planes which are perpendicular to x-axis. Okay, for x constant positive, they will be on the positive direction perpendicular on this side, and if x is equal to constant with constant negative, they will be on the negative axis. Okay, and similar to this. Okay, also we can have planes which are not parallel or perpendicular to axis but are at some angles. For example, this plane z is equal to x minus 20. Okay, so this is a plane which is not parallel to any axis, but because y is not there, so this plane for every point x the z value will be same on the y direction. Okay, so at x is equal to 20 z will be 0, so this is x 20 z 0, and this is true for every point y. Okay, and then it increases on this side as x increases, and it goes downward on the other side when x is towards the negative axis. Okay, so it's a slant plane. And similarly we can have planes which can cross both x and y axis. So like z is equal to x minus y minus 10. So when uh, in the positive direction of x-axis and negative direction of y-axis, so when y takes negative values, then these both will add up and z will increase. Okay, so in this direction where y is negative and x is positive, it is going up side, and when x is negative and y is positive, then this will be negative, so z will increase negatively. So this is y positive and x negative, so in on this direction it is going downward. Okay, so it's again a slant plane crossing at some point on the x and y axis. Okay, so we can draw planes in 3 dimension, and these are basic equations: z0, x0, y0. These are the planes perpendicular to the uh, z-axis and x-axis and y-axis, and they are slant planes. Okay, so general equation of plane is like ax plus by plus cz equal to d. Okay, then also there are some common surfaces. Z is equal to f of xy, or f of xy is equal to constant, and I'm going to show you some of the three-dimensional surface plots. And first of them is ellipsoid, which is given by x square by a square plus y square by b square plus z square by c square is equal to constant. Okay, so uh, uh, for any z value, like they are ellipses, or any y value they are ellipses. Okay, so you can see that they are forming ellipses in all directions. Okay, and when a and b equals c, then it is the equation of sphere. Okay, so sphere is a special case of ellipsoid when a equals b equals c. Okay, the second is the hyperboloid of one sheet and two sheets. So this is the hyperboloid of one sheet, which is x square by a square plus y square by b square minus z square by c square is equal to 1. Okay, so one of the variable coefficient is negative and the other two are positive. Okay, and the hyperboloid is open in the direction of the variable which has a negative sign linked to it. Okay, so this equation is for a hyperboloid of one sheet where hyperboloid is open towards the z-axis. Okay, and if you want the hyperboloid to be open towards the x-axis or y-axis, then we can choose the negative sign on that side, and so two positive and one negative should be there. Okay, so if we have minus of x square by a square and plus here and plus here, then this hyperboloid will be open in the direction of x-axis. Okay, then the hyperboloid of two sheets. So in one sheet you have one negative sign and two positive. This reverses in hyperboloid of two sheets. Okay, so in hyperboloid of two sheets we have one positive sign and two negative signs. Okay, and the hyperboloid of two sheets is open in the direction in which the positive sign is there. So for this particular equation, hyperboloid of two sheets will be open towards the z direction. Okay, like this. So this is the z direction. Okay, this is the x direction and y direction. So it's a hyperboloid of two sheets, and it is open in the z direction. And if we just need to take one side of this, the upper hyperboloid or the lower hyperboloid, then we can solve this for say z, and the will get a plus minus sign with the root. So the positive value of root will give us the upper hyperboloid, and the root value with a negative sign will be the lower hyperboloid. Okay, and also if you want this to open in the direction of x or y, then accordingly we can choose the positive sign. Okay, so if we have a positive with x square and negative with y and z, then it will be a hyperboloid in the direction of x-axis. Okay. The third example is of cylinders. Okay. And this is a elliptic cylinder here, typical x square by a square plus y square by b square is equal to 1. So we know that is the equation of ellipse. Okay. But in not in we are not in 2 dimension, we are in 3 dimension, and this equation if holds for all x y z, then because z is not there, so this will be a cylinder whose direction extends in the z direction. Okay. So like this is the x-axis, y-axis, and this is the z-axis. So it is a x square by a square plus y square by b square equal to 1. Okay. So ellipse on the xy plane, and that ellipse extends in the direction of z, because this is true for all z. Okay. So you can see that this the elliptic shape. The cross section here is elliptic. Okay. And in case a equals b, then this will be a circular cylinder. Just for example, here we have drawn this as a circular cylinder with the open along this z axis. Okay. So if you want this cylinder to be open along this x axis, then we only need to write this equation in terms of y and z. Okay. So if you have equation like y square plus z square equal to 1, so that will be a circular cylinder open in the direction of x axis. Okay. So accordingly we can write the equation of cylinders. Okay. And to point out here that these are not only the cylinders like the elliptical or circular, we can even have parabolic cylinders. So if I define y is equal to x square to be the curve on the xy plane, which holds for all z value, then that parabola which will extend in all z directions, so that will also be a cylinder, and we can call it a parabolic cylinder. Okay. So basically any curve on the xy plane if I draw which hold for all z values, then that will form a cylinder. Okay. So we can call that a cylinder. Okay. uh, the fourth one is a cone. Okay. So which is z square by c square equal to x square by a square plus y square by b square, and it is open along z. Okay. So the variable on the one side. Okay. So it is open along this z direction. If you want it to be open along x or y, then you can write it as x square is equal to x square by a square say equal to y square by b square plus z square by c square, then it will be open along the x axis, and similarly it can open along the y axis. Okay. Say for example in this case it is this open towards the z axis is a cone. Okay. So and its upper cross section is made circular. Okay. So the for the case when a equals b. Okay. So when a equals b, this cone will have a circular cross section on this side here. Okay. So this is formed with a circular cross section, or you can have a elliptical cross section if a is not equal to b. Okay. So it's a typical cone which is open along the z direction. Okay. So there are this one piece of cone which is above the xy plane, and other which is below the xy plane, and if we only want to plot the one out of the two, then we can solve this equation for z. Okay. So there will be a plus minus root. Okay. So the plus sign root will be the cone portion which is above the xy plane, and the negative sign root will be the cone portion which is below the xy plane. Okay. And similarly, as I said, we can have cones which are open along different directions. Okay. So this particular cone is for z square equal to x square plus y square, so it has a circular cross section here. Okay. And if we want to have one open along the x-axis, then we can write it in this way. Okay. So here I am defining only circular, but you can also define elliptical by dividing with a square and dividing with b square. Okay. So it will look like this. Okay. So this is the z-axis, the x-axis, and this is the y-axis. So it is open along the x-axis, and because x square is defined in terms of y and z. Okay. And it has a circular cross section. Okay. Then we can also define paraboloids, and the This is a typical equation of elliptic paraboloid, where equation says z by c is equal to x square by a square plus y square by b square. Okay, so on this side you can see that it is like equation of ellipse, so it is a elliptical paraboloid, and if a equals b, then it will become a circular paraboloid. Okay, so here you can see that we have drawn is a circular paraboloid. Okay, so if y is fixed, it is like z is equal to x square, and if x is fixed, it is z is equal to y square. Okay, so with z there is the parabola z is equal to x square or z is equal to y square. Okay, and for a fixed z, it is like ellipse. Okay, so at a fixed height it will form like a ellipse here. Okay, in this case a equals b, so it is forming a circle here. Okay, so the also to be noted is the this paraboloid here is drawn in the upward positive direction of z. Okay, so that means c is taken to be positive. If c is negative, okay, the sign of c, then this paraboloid will be a downward paraboloid. Okay, uh, finally, we can have hyperbolic paraboloids, which are z over c is equal to x square a square minus y square by b square. Okay, and hyperbolic paraboloid will look like this. Okay, so there is, like you can see, there is a parabola. Okay, for uh, y fixed there is a parabola z is equal to x square, and for x fixed it is z is equal to minus y square. Okay, so on one side is a upward parabola, on the other side there is a downward parabola, and for z fixed you can see that there is a hyperbola. Okay, so for height fixed you can see there will be a hyperbola formed on both sides. Okay, this hyperbola here. Okay, so this is a hyperbolic paraboloid. Okay, and so these are some of the basic surface plots for some common known surfaces. Okay, now we are going to define what are level curves and contours for functions of two variables. So first, what are level curves? The set of points in the plane where a function fxy has a constant value fxy is equal to constant is called a level curve of function. Okay, so level curves are those curves where function values are constant. Okay, so how we can calculate those level curves? The curve in space in which the plane z is equal to constant cuts a surface z is equal to fxy, okay, is made up of points that represent the function value fxy is equal to constant. Okay, so if you are given any surface z is equal to fxy, okay, and if I cut that surface with a plane z is equal to constant, okay, then the point of intersection of these two will be a curve in space, which, and the equation of that curve will be this fxy is equal to constant, and so that curve will be the level curve. Okay, for this surface c is equal to fxy. And what are contours then? Okay, so the map of level curves is a contour plot. Okay, so if I plot a map of all the level curves for a function, then it will be a contour plot. Okay, so let us see this through as example. Say I take a surface z is equal to 4x square plus y square into e raised to power minus x square minus y square. Okay, so this function is plotted on the xyz okay coordinates. Okay, so this is the x-axis, this is the y-axis, and this is the z-axis. So we plot this surface on this space. So it says that if you have a surface, so you have a surface now this. Okay, so and if a plane z is equal to constant cuts this surface. Okay, so say I cut this with a z is equal to half plane. Okay, so z is equal to half will be parallel to xy plane. Okay, so if I cut with z is equal to half this plane, this surface z is equal to fxy, then you can see that the point of intersection of these two is a boundary here. Okay, this boundary. Okay, which will go on the other side and come back here. Okay, similarly there is another boundary here. Okay, so this along this boundary the function value is constant. Okay, so this curve is the level curve for the surface. Okay, similarly we can cut at different heights for z is equal to constant. So if I cut it here, okay, so there will be a boundary formed here. Okay, that will be another level curve. Okay, similarly if I cut it here, okay, so there will be another boundary here, okay, on both sides, and that will be another level curve. Okay, so with different z values, z is equal to constant, if we cut this surface at different heights, then you will see that different boundaries will form. Okay, and different curves will form, and these curves are level curves. Okay, so what we mean is that along this curve the function value will not change. Okay, so along this curve the function value remains constant. Okay, so the function value will not change. That's why we call it a level curve, because it's a curve which is at level, means the function value on this curve is a fixed value. Okay, constant value. Okay, so what are contours now? Okay, contours are their map. Okay, so if you look this surface from the top, from the z-axis, this will look like this. Okay, so this is the z-axis, is x-axis, y-axis. So if you look at the surface as a top from the top, okay, so if you look at a top view angle, then you can see the surface as well as the level curves. Okay, so if I plot these level curves on the xy plane, okay, on the domain, okay, then these level curves will look like these curve. Okay, and this is what we call contour. Okay, so contour is actually map of the level curve. Okay, so that means if we plot the level curve on the xy plane graph, okay, then this graph is called the contour of the surface. Okay, say for example, I take one more example here. Consider the function z is equal to 100 minus x square minus y square. So now you know what exactly this means. This is z on this side minus x square minus y square. Okay, so there is a downward paraboloid. Okay, and let z is equal to 75. So there is a plane, okay, which cuts the surface to generate a level curve. Okay, so plane when cuts a surface, it generates a level curve. Okay, similarly if I take different constant values, z is equal to constant, it will generate more level curves. Okay, and so for example if we plot z is equal to 100 minus x square minus y square, so it will be this paraboloid. Okay, and z is equal to 75 is a plane which cuts this. Okay, so the boundary formed will be this. Okay, so this boundary is the level curve for the surface at z is equal to 75. Okay, and the contour is the map on the xy plane. So we can also say that contour is the projection of level curve on the domain plane. Okay, so if I project this and plot this level curve on the xy plane, then this is the contour. Okay, so similarly we can cut this at different heights. Okay, and those all will be level curves, and if we plot all those on the xy plane, so the on the xy plane all the curves that we plot, they will form the contour. Okay, so for this paraboloid, if I cut it at different heights and plot them on the xy plane, so is x-axis, y-axis, then they will be circles. Okay, so contour plot of this paraboloid is actually circles. Okay, so you can see that here this boundary of level curve is a circle. Okay, so at any height, if you cut this, it will generate a circle, because when I substitute z is equal to constant here, then you can see that it is x square plus y square is 100 minus constant. Okay, so it is like x square plus y square equal to some constant, so it will generate circles. Okay, so this is the contour plot. Okay, so contours are on the xy plane, and this is the level curve. Okay, similarly we can cut different places to generate level curves, and correspondingly we can plot the contours. Okay, and then the second definition is the level surfaces for functions of three variables. Okay, so just like in two variables we can have level curves, in three variables we can have level surfaces. Okay, so the set of points x, y, z in space where a function of three independent variable has a constant value f, x, y, z is equal to constant is called a level surface of f. Okay, so if you are given w is equal to f, x, y, z, then if I put w is equal to constant, then fxyz equal to constant becomes the level surface of the function. Okay, say for example describe the level surface for the function this w is equal to root of x square plus y square plus z square. So method says that if I cut this using w is equal to constant, then this is fxyz equal to constant becomes our level surface. Okay, so the level surface for this is root of x square plus y square plus z square is equal to constant. Okay, so immediately you can see that they are spheres. Okay. Okay, so remember this is a geometry in 4 dimensions, so we cannot plot it. Okay, so the geometry is in 4 dimension. We can visualize them using their level surfaces in 3 dimensions. Okay, so these are spheres. So with different constant value, I can generate different level surfaces. For example, these are spheres of different radius. Okay, so I have generated here 3 spheres of different radius. This outermost is of radius 4, then there is the inner which is of radius 2, and then there is a inner inside blue which is of radius 1. Okay, so by level surface we mean that if we move on say this outer sphere anywhere, okay, the value of function will not change. Okay, so because it's a level surface means that a surface on which the value of function will not change. Okay, so on this outer surface if I move anywhere from one point to another point, the value of function will not change. Okay, similarly on the inner sphere, if I am on this sphere and I move from any point to any point on this sphere, then the value of this function will not change while moving from one point to another. But if I move from one surface to another surface, say this surface to this surface, then the value of the this function will change. Okay, so moving from one to another surface the value will change, but moving on the same surface the value of function will not change because they are level surfaces. Okay, so that's one interpretation of this. Okay, so with this I close this first topic on 2 dimensional and 3 dimensional. Okay, we'll talk about limit and continuity of functions of 2 dimension in our next lecture. Okay, have a very good day till then.